Hi, so in this video, I want to focus on non-equilibrated systems or perhaps reactions which were once equilibrated, but then when they are, kind of messed around with, if we do anything kind of funky with them, right, how they would then respond to hopefully reach equilibrium once more. So for this, I want us to consider just an example reaction right here of, say, 1 mole of A producing 2 moles of B, both in the gas phase, and let's say that for this reaction, the equilibrium constant K is equal to 12. Now, when this reaction is equilibrated, right, we can kind of think of it as essentially a balance between our products and reactants. This isn't necessarily to say that we have the same amount of products versus reactants, right? That depends on the relative size of the K constant, but just as kind of an analogy right here, I think of it as like the desired proportions. Those are what is in balance here on my little scale. And so, right, if we do have everything at equilibrium, that's to say that the reaction quotient Q is perfectly matching with K, right? Whenever we're calculating out the reaction quotient, that doesn't necessarily have the same constrictions as K does, right? The reaction quotient can be determined with any concentrations of products and reactants, not necessarily the equilibrium ones, so not necessarily already equilibrated. But sometimes we luck out and we do calculate that reaction quotient and it already matches K as it does right here. This indicates to us then that the reaction is already at equilibrium. And so if we were to allow this reaction to kind of sit for some amount of time, what we would see is no real change in the concentration of A or B. Those concentrations are effectively done changing. While equilibrium is a dynamic process and there's still this forward and reverse reaction going on, those forward and reverse reactions are going at the same rate, and so there's no change overall to what we observe as the concentration of either our products or reactants. Now compare this instead to a different scenario. So instead, right here, I have on my little balance, again, some amount of A and some amount of B. But as you can see from the little balance here, it seems like there's a little bit more A or less B than what would be necessarily desired. What this means is that the reaction quotient Q is going to end up being less than K, right? We effectively have more reactants than we want or less products than we want, giving us a smaller Q value. And so because there are, say, too many reactants or too few products, how this reaction is going to proceed is by trying to make more products, right, in order to regain that balance. So right, because things are kind of tilted off to the A side here, right, it's going to try to make up for that loss and instead start producing some B. Just if we allow this reaction to kind of sit over time, that's the effect that we would see. Now, the language that we use to kind of describe that movement towards the products, I've written out right here as shifts right, right? If we think of the reaction going from reactants on the left to products on the right, then right as this reaction proceeds, because we are making more products, it's going to shift to the right. It's going to make more of those products and kind of lean towards that side. And now finally, we can imagine maybe a reverse scenario where instead I have too large of a Q value, that is like too many products or too few reactants. And so again, in response here, if I have this third scenario where I have that imbalance, right, what the reaction is going to do is try to respond to make up for that imbalance, in this case, shifting left to make more of our reactants, again, just trying to restore that balance between the two. Understanding this kind of like shift is important for when we're looking at different ice tables and things, right? Knowing exactly like how the change is going to occur, whether that's like a positive change for the products or a positive change for the reactants, right? Being able to compare Q, the reaction quotient, versus K, the equilibrium constant, is very essential for that step. But we can think about it a little bit more qualitatively as we're doing right here, right? And as we'll see in some other examples as well, just kind of thinking a little bit more on the conceptual side is helpful for us to know, what a reaction is going to do. So this brings us to this idea where, if I have a reaction that is at equilibrium, it's happy, it's not going to change at all. But I can do things to it, or some outside force can do things to that reaction that will knock it out of equilibrium. These are referred to as different stresses that can be applied to an equilibrium. So a stress may be adding or removing products or reactants. A stress may include changing the volume of our system, thus changing essentially the concentrations of our products and reactants, or even changing the temperature of our reaction. These are all stresses that our reaction mixture may experience, and those stresses can disturb it enough to basically not be in equilibrium anymore. And so there's this idea that, right, if the system is no longer in equilibrium, then it's going to respond by either shifting left or shifting right, trying to make up for that disturbance, right, or trying to negate whatever stress happened to it. This is known as Le Chatelier's principle, and it basically says that when a system is stressed, it will respond in an attempt to relieve that stress, right? Whatever that stress may be, if it's one of these three different changes, right, we can imagine how the reaction is going to shift in order to bring balance back to the overall reaction. So let's walk through those different scenarios and see maybe how those different stresses are going to have then a different response from the system. So first here we can consider what happens when we remove products from an already equilibrated system. So again, I have like A turning into 2B here, and let's say to start, right, I already have this perfect equilibrated happy mixture. I have the perfect amount of products and reactants, and so this equilibrium is unbothered, it is undisturbed, it is totally good. But some outside stressor goes in and it messes with the equilibrium. Perhaps it scoops away some of the product here, it flushes out some of the B that's in there, and so as a result, right now we have that imbalance. We essentially have too much reactant and too few product, and so now the system is stressed. As we saw before, this imbalance is going to cause a shift to the right, in order to balance things out again. Basically what we're going to see is the reaction responding by producing more products and using up some of the reactants. What that does is it fills in the gap that was left by removing the products, right? Basically, if a stressor comes in and removes products, the equilibrium responds by making more products and shifting right. You can imagine then a similar scenario where instead I remove reactants as a stressor to my already equilibrated system. If I were to remove reactant, what that causes then is an imbalance favoring the products. Again, because we're trying to restore balance to the system, in response, my reaction is going to shift left, thus making more reactants, using up some of the products, and again getting to that more balanced, equilibrated state. So, right, you can see how like removing anything from the reaction is going to cause the equilibrium itself to kind of try to make up what has been removed, right? It's going to try to fill in the gap that's left there. In the same way, when you add products or you add reactants to an equilibrium, well, that kind of knocks things out of balance, right? The reaction is again just going to respond in a way to basically make lemons out of lemonade. Here I propose a situation where I'm adding product. I'm essentially overwhelming the product side, making it way too heavy on the product end of this. And so naturally what the reaction is going to do is it's going to take those products, it's going to convert them into reactants, thus restoring balance. You can imagine then maybe what would happen if instead I had my perfectly equilibrated system and I added reactants to that. You can ask yourself like, which direction will the reaction shift if we were to add more reactants to an equilibrated system? So by adding more reactants, that's going to knock the balance out so that we have too many reactants and too few products. And so naturally the reaction is going to shift to the right. It's going to try to make up for that imbalance and thus use the reactants that were given to it. So when we're adding anything to an already equilibrated reaction, basically imagine that thing that was added, it's going to react, whether that be like a reactant turning into a product, or if we add in products, as we see right here, right, then that's going to turn into a reactant, right? It's again going to try to just make something out of what was given to it. So when we add something, imagine how that thing can be used, right? Again, to try to restore the proper balance of products and reactants. Now, this change or these stresses can be rather intuitive in terms of like changing the amount of products or reactants, right? Throwing off that balance and trying to restore balance. But another stress that was mentioned was how volume may affect the equilibrium. So to picture this, right, imagine here I have a nice little box like so, again with my balance of products and reactants, and currently this box is at equilibrium, right? I have just the right amount of everything in there. Now let's say that I can take this box and I can compress it down, so make the volume smaller. If I compress everything, what I've done here is I've changed the concentrations of both the products and the reactants. Now you may be thinking, well, if we change both of those concentrations, they're both affected in the same way. It's the same volume change, so it shouldn't have any change on the actual reaction quotient. But that's not necessarily the case, right? Because we have, say, these different molar coefficients of B versus A, right? Although we're changing the concentration of both B and A by the same amount within our reaction quotient and within our K expression, right? That change is going to be squared for B versus just to the first power for A based off of their molar coefficients. And so what that means here is that even though I've compressed everything by the same amount and I've changed the volume by the same amount, what I essentially see here is a reaction quotient that is larger than K, thus meaning that I need to make more of my reactants and less of my products, or I essentially have it too heavy on the product side right now. And so given some time, this reaction is going to respond by making more A and less B, thus restoring balance once more. Now, in a more like generalized form, right, we can think of the effect of compression in this way, where anytime we compress or we decrease the volume of our system, the reaction is going to shift towards the side with a lower summed molar coefficient. So when I say summed molar coefficient here, I mean like all of the molar coefficients on the reactants versus all of the molar coefficients in the products, right? Whichever one is lower, that's the side that is favored or pushed towards when we compress the volume, like we see right here. This is ignoring any solids or liquids because, again, those things don't count towards our Q expression or our K expression at all. But looking at just like gases and aqueous species, if we compare the molar coefficients in total there, when we compress the system, it's going to shift towards the side with the lower summed molar coefficient. In the opposite way, right, if we were to expand, so have instead an increase in volume, or commonly like if we're looking at aqueous solutions, then like a dilution scenario, if we're to expand our system, then the equilibrium responds by shifting to the side with more molar coefficients, right, or a higher summed molar coefficient. So how I made sense of this, not necessarily in terms of like concentrations and how that affects Q or K, but instead in just like a more conceptual, like energetic understanding of what's going on here, right? Imagine when I compress the volume like we see right here. What that's doing is it's forcing all of the particles to be much closer together. And what that means then is that the particles are going to bounce into each other at a lot higher frequency than they did when they were more spaced out. And so with each of those collisions, we are essentially raising the energy of the system, right? With each bump, it's going to have higher energy. And as we've kind of discussed before, right, things generally like to be at lower energy states. So by forcing everything together, you're kind of making the system be higher in energy than it actually wants to be. And so to make up for that, right, what it's going to try to do is just make less particles overall. That's going to give you then less bumps, right, and less collisions. And so that's kind of how I made sense of what happens right here. After compressing my box, I basically have a lot more collisions happening because the particles are much closer together. And so then it made sense that the B particles that are in there would instead combine back together to make A, because then we just have a fewer number of molecules overall, or a fewer number of particles actually bumping into each other. So thinking of this purely from like an energetics perspective, if we're to decrease the volume, we're basically increasing the energy of the collisions in there, also like increasing the pressure or increasing the concentrations of our products and reactants. And so, right, in response to that, it's going to favor the side that just makes less of those things, right? Less collisions, less particles, all of that stuff. Okay, now lastly, what I want us to look at is the effect of temperature as a stressor as well. So as we've discussed previously, right, temperature has an effect on things like the rate of a reaction, right? Changes the rate constant associated with a reaction. A change in temperature is generally going to speed up a reaction, so it's going to decrease the rate constant. What that also means is that the equilibrium constant is going to change as well. Now we'll see exactly how the equilibrium constant relates to temperature, how exactly it changes. We can actually calculate that through an equation that we'll see in another lecture. But here I just want us to think about it a little bit more just conceptually, a little bit more qualitatively, right? How the temperature is going to affect the equilibrium of a system, right? And how that's going to either shift the reaction to the left or shift it to the right. So to rationalize this, what I like to do is I like to think of changing the temperature as essentially adding or removing heat from our system, right? In essence, that's what we're doing. When we're raising the temperature of a system, we're adding heat to it in some way. And so depending on if the reaction itself is like endo or exothermic, that's kind of as if we are adding a reactant or we're adding a product. So for instance, right, if I have like an exothermic reaction, I think of heat as essentially a product in an exothermic reaction. As a reminder, exothermic reactions will release heat as they progress. And so take for example right here, I have this reaction of sodium and acetate ions reacting to form sodium acetate in the solid phase, and also produced with that is some heat. So, right, this has a negative enthalpy of reaction. This is an exothermic process. So I want you to kind of ponder here, like, if I were to say, take this equilibrium right here and say it's at equilibrium, but then I mess with it and I raise the temperature of the system, how is it going to respond? Will it start shifting towards the products or towards the reactants? Go ahead and take a moment to think about this, and then we'll discuss in just a minute. So thinking here again with like how raising the temperature is essentially like adding heat to a system. In this case, I would be like adding a product to my already equilibrated system because this is an exothermic process. As we saw before, if we add products to a reaction, how it's going to respond is by shifting in the opposite way. So it's going to shift towards the reactants, right? What I would expect to see for this equilibrium is, right, when I'm raising the temperature, it's going to push to the left, right? It's going to respond by making more reactants because I've added that heat into the reaction. And so, right, you can imagine kind of similar scenarios, perhaps if we're to cool down a reaction or if the reaction were endothermic instead, right, that's going to have a different effect. But right, through this kind of rationalization of simply thinking of heat as similar to a product or a reactant, right, that can kind of help to make sense of how this change kind of knocks a system out of equilibrium and then how that system would respond. So to kind of close this out, I just want to walk through like a few scenarios right here, applying Le Chatelier's principle. So here, imagine this reaction where I have 1 mole of N2 and 3 moles of H2, producing 2 moles of NH3. And then I also give the enthalpy of reaction here as being a negative value, right? Something less than 0. So right, I want us to imagine a few different scenarios or a few different stresses that I can do to this reaction. So imagining here that the reaction is already at equilibrium. If I were to remove hydrogen from that, how will the reaction respond? Do you think that the equilibrium will shift to the reactants, to the products, or will there be no change at all? So in this case, right, because I am removing a reactant, the equilibrium wants to make up for that loss. And so we would expect to see the equilibrium shift towards the reactants as time progresses. After I've removed this hydrogen from the reaction mixture, it's going to make up for that lost hydrogen and also make some additional nitrogen as well. If instead I were to add nitrogen to an already equilibrated reaction mixture, how would the equilibrium respond in that case? So in this case, right, kind of have the opposite effect. Because I'm adding in a reactant, the reaction is going to use that up, thus making more products, right, shifting to the right for this equation. if I were to lower the temperature of the reaction. So again, if I have this already perfectly equilibrated, but I drop the temperature down, the equilibrium will shift to the products, right? Because this is, again, an exothermic reaction. We know this because delta H is a negative value. So, right, think of heat here as basically a product. By removing heat or lowering the temperature, we need to make up for that loss of product. So, right, the equilibrium is going to respond by shifting to the right, thus making more products. Now, lastly, if I were to say increase the volume that this reaction mixture is in, how will the equilibrium respond to that stress? So in response to an increase in volume, remember that the reaction is going to tend towards the side with greater molar coefficient, right? So we have basically more space, we can make more particles. And so in this case, that favors the reactants, right? Because our summed molar coefficients on the left side is 4 versus 2 on the right side, right? It's going to favor the higher molar coefficient side. So in this case, our reactants. All right, but so those are, again, like the different ways in which we can kind of mess with an equilibrated system and see how it will respond. This is again known as Le Chatelier's principle, right? This idea that a system knocked out of equilibrium will respond in a way to try to, again, achieve equilibrium. But so please let me know if you have any questions, and I'm always happy to help. Bye.